This is a presentation for EE4593 Internet of Things Security. I am James Ryan, and this is my presentation for the midterm project. This is a smart parking lot system. On the screen, you can see some information, my email. Please reach out and email me with any questions, comments, or concerns you have, as well as a link to a GitHub repository, which I will talk more about later. So why am I doing a smart parking lot system? If you're like me, when you go to UTSA, when we're on campus, you often want to park in Bowerly Road, Lot 1. The problem with this parking lot is, it always looks full, but sometimes there's one or two spots open, and you have to drive through the whole parking lot to find them. I, quite often, end up driving through the whole parking lot, looking for that one or two spot that I think is open. This ends up wasting 3 or 4, maybe 5 or 6 minutes, depending on whether there's a spot open or not, that I could have used to just go park in a different parking lot and take that time to take the bus or to walk to campus. I don't really like that. I would much rather, when I drive up to the parking lot, be able to look at a sign and see, are there any spaces open? There are also some existing alternate solutions. There is some solutions that have a sensor in every parking spot that detects whether that spot is occupied. A problem with this is it's expensive. You end up needing lots of different sensors, obviously, one for every parking spot. There are also some systems that use a single camera overlooking the whole lot, and then some image recognition technology to work out how many spots there are, how many are occupied. The problem I have with this is, this ends up collecting a lot of personal information, and if that system were to be compromised, there's lots of personal information there that could be used for malicious purposes. So moving on to the goals for this project, I wanted to only have a few sensors. I ended up with 2 sensors and a display and a gateway. So there's only about 4 parts in this project. This helps keep the cost down. My cost for this was only a couple $100s for all of this. It also makes it easier to maintain and to deploy. There's only a few things you need to set up. There's also fewer points of failure. If something dies, there's only a few components that can go wrong, and so it speeds up the process of maintenance much more. I also didn't want to collect any personal data. As I've talked about before with that camera, if you're collecting personal data, you have to do a lot of storage of that data, and it can also be pretty bad if your system is compromised. Without collecting personal data, you don't really need to comply with any privacy legislation because you don't have any identifying information. There's fewer risks if your system is compromised. The worst case scenario for this system being compromised is it shows that the parking lot has spaces when it doesn't, and so people waste 5 or 6 minutes of their day driving around a parking lot. You also don't need to collect any data. I don't really see a reason to use a whole camera for this. To use a security camera to track the occupancy of the parking lot, you don't really need an image of everything. This system is, I think, much simpler and much cleaner. So let's go on to the design. There are 3 principal components. There is a server that tracks the parking lot occupancy. There are some sensors, and these sensors will inform the server when vehicles enter and exit. There is also a display that informs parkers of the occupancy of the parking lot. For this project, I'm using a proof of concept display, just a 2 by 16 LCD display. If this were to be deployed at the Bowerly Road parking lot, I would recommend installation of a Jumbotron. Let's talk about some of the Internet of Things technologies I'm using. So to communicate between the gateway and the nodes, I'm using LoRaWAN. So the gateway will communicate with the 2 sensors as well as the display over LoRaWAN. And then, for communication between the server and the gateway, not between the server and the nodes, between the server and the gateway, I'm using an MQTT broker. So let's talk about some of the hardware involved in this. There is a Raspberry Pi 4 for the server. It is the 4GB model. It's the Raspberry Pi 4B. On that Raspberry Pi 4 is also the LoRa gateway, which is a RAC 2243 Raspberry Pi hat. There is also, for the sensors, the Elegoo Mega 2560 R3. This is compatible with the Arduino Mega 2560 R3. It's the same processor, so there's lots of existing libraries already that deal with this board, which makes it much easier to program and get up and running. On the sensors, I'm using a Seed ultrasonic distance sensor. This is just a distance sensor. And then on the sensors as well as the display, I'm using the LoRa Arduino hat. This is an RAK811. This allows the Arduinos to communicate with the gateway over LoRaWAN. For the display, in addition to another Elegoo Arduino and the LoRa hat, there is also an LCM 1602 2-line by 16 LCD display. These are very common. Virtually all 2-line by 16 LCD displays work exactly the same. Okay, so here's some images. These are the two sensors. You can see in blue the Arduino / Elegoo, in black the RAK811 development boards, and on the sides you can see the distance sensors. This is the display. Because it's just a 2-line by 16 LCD display, it's just stuck on a breadboard, and you can see connected to that is the RAK811 and the Arduino. And this is the RAK gateway and Raspberry Pi. It's the RAK2243 gateway, version A of the board, and it is connected to a Raspberry Pi 4B 4GB model. So now I'm going to cut to some videos walking through the sensor firmware as well as the display firmware. This is a walkthrough of the firmware for the display. It's in a file helpfully named display.ino, which of course you can find, as with all the other firmware, in the GitHub. So, in this firmware, we're setting up some global variables that are used by different things throughout the code. So we are getting the network and application session keys, as well as the device address. Those are going to be coming from a file secrets.h that is not in the GitHub. You'll have to declare that for yourself, because those are secrets that shouldn't be shared. Don't make those public. Then we are just doing a define here. This LoRaWAN class C is only really used in this file, so it doesn't make sense to define it somewhere else. We are then setting up a serial port between the RAK and the Arduino, as well as setting up the liquid crystal library for here. And then we are declaring the RAK object, as well as a function we'll use later on. In this setup function, which is called once when the device is powered on and never again, we initialize our connection with the LCD. If we are in debug mode, we will try and initialize a serial port connection to some attached computer. And if we're not, we won't do that. Then we will open the serial port with the rack, wait a couple seconds for everything to initialize, and then begin setting all the parameters we need there. So we'll set the LoRaWAN class, we'll set the work mode to LoRaWAN, we will initialize the LoRaWAN, which will set up the join mode. We're using activation by personalization. It will set the region we're working in. In our case, we're in the US, or somewhere around 915 megahertz, as well as setting the device address, network session key, and app session key. We will attempt to join a network, and we will just keep trying to join a network until we're able to. And then we will set the package type. In our case, we're confirming all packages. We then need to send a single packet just to open the receive windows. Once we've opened those, we are working in LoRa class C, so of course we're just listening all the time for data coming in, and we don't need to send a packet out to open our receive windows again. Once that setup function is called, we will call the loop function, and when the loop function returns, it will just be called again, and this will just be called continuously. So in this loop function, there's an explanation of how we're not really doing any error checking here. In a more full-featured project, we would be doing quite a bit of error checking, but we're not doing that here. In this loop function, we are getting some data from the rack, and then stripping the data so that only what we're interested in, which would be data sent to us by the application that's running on the gateway, only that data is used from here on out. We don't care about any of the LoRa specific data. So if we have any such data, then it's encoded in hex format, so we will convert that into a string and then print the string on the LCD. After that, we will wait 1 second, and then this function will be called again, and that will continue on. This is the walkthrough for the sensor firmware. It's very similar for virtually all of the setup to the display firmware, so I'm not going to go over that too much. I will mention up here that we are joining with activation by personalization, which is not the best way to join. Because when you join in ABP mode, you are hard coding the device network session key and the device application session key. If those are ever leaked, then anyone can read all of the LoRa packets you're sending, which for something like this isn't a huge deal. But if you were sending any important data, or if you were sending if you were working in a project that's more important, you wouldn't want to do this. You would want to use over-the-air activation, which would hard code a application and device ID, and then every time the device is activated, it will generate an application and network session key to communicate for that session. And so we are, again, getting the network and application session keys and device address from a secret file. And then we are going through virtually the same setup process that we did for the display. So in our loop function, there's another mention here of, in this whole project, we're not really keeping track of the frame count. That's a very good thing when you're just setting up the project, because it means you don't have to worry about any of that. But because we're not counting LoRa frames, we are vulnerable to a replay attack. So a malicious device doesn't need to know anything about our application or network session keys. It could just capture one packet and then send a whole bunch of copies of that packet. And because we're not using a frame counter, there's no encoding of this is packet 1, this is packet 2, this is packet 3. All of these packets can just be sent, and the server sees, oh, I see the same packet again. Oh, I see the same packet again. There's just a quick mention of we should really not be doing that. We should really be keeping track of the frame counts. Inside this loop function, we are figuring out the distance that our distance sensor measures. If it is within some range, which for this purpose is between 1.5 and 3.8 meters. If it is within the range, we're going to wake up the rack, format the data correctly, and send it off, and then put the rack back to sleep and wait for 1 second before trying to read the sensor again, so we don't read the same vehicle entering twice. And that is really all we're doing in the sensor firmware. So now let's talk about some of the software. There are, on the rack gateway, there is the LoRaWAN software, which is the ChirpStack packet forwarder, network server, and application server. There's also an MQTT broker. I believe it uses Mosquito. And the operating system the rack ships with comes with the ChirpStack and MQTT broker pre-configured to talk to each other. There is also the parking lot server, which also runs on the gateway, although it doesn't have to. You could run it over the network and connect to the broker that way. But this server communicates only with Mosquito. It does not concern itself with the sensors. It doesn't care about the display. It only communicates with the Mosquito MQTT broker. So now I'm going to go to the ChirpStack software walkthrough. Okay, this is the walkthrough of the ChirpStack configuration that I'm using. So in ChirpStack, which helpfully provides you with a very convenient web console to go through, you can see that inside the IoT Security project application, there are 3 devices, a display, a left sensor, and a right sensor. And all of those sensors were seen some time ago. For the display, This is the display. You can see all the LoRaWAN frames here. It sent its first packet to us, and then it doesn't send any more packets. It just waits for a response from the server. And so we only have one packet. Whereas for the sensors, because they are currently just pointing at a wall an appropriate distance away so that they will continue sending data, you can see that each of the sensors is just sending data every time it can. And so let's go through the configuration of this real quick. So for the application configuration, that's just the name. Each device is where it gets interesting. So each device is configured with a certain profile. In this case, all of these devices are using the activation by personalization profile. And of course, we are disabling frame counter validation because we are not doing any tracking of the frame counter on either side. After that, the only other thing here is there is the device address. Every device will have a device address, as well as a network and application session key, and these are things used by activation by personalization. That is all that we've really done on TripStack. This is the walkthrough for the server code. The server runs on the gateway, and it doesn't have to run on the gateway because we're publishing topics to MQTT, but it's much simpler to run it on the gateway. You're not worrying about what is the gateway's IP address, making sure you're connected to the gateway and all that. And so we have the server running on the gateway. The server is fairly simple. It doesn't do much error checking. It doesn't do much resiliency. Much like the rest of the project, it serves as a good demonstration. Were this to actually be deployed as a full solution, there would be a lot more work that would need to go into this. Additionally, because this server is not posted on the GitHub, there's not a whole lot of explanation about why we're not doing all that error checking. There's not a whole lot of explanation about where that error checking could be done. Because this isn't meant to be shared publicly, this is really just meant just for this project and won't be worked on in the future. So, for this server, when we first enter, we will set up some functions. We will get the device addresses. These are for the LoRa nodes that are the left and right sensors as well as the display. We will set some user data used by our client object. We're using the Paho MQTT client library. You may be familiar with that. This data is just going to hold whether the left and right sensors have been updated and an additional flag to tell whether any sensor has been updated. We'll establish a connection to the MQTT broker. And so whenever this connects, on our connection to this MQTT broker, we will log that we've been connected, and then we will subscribe to our topic and add the message callbacks for the left and right sensors. So because we subscribe, as explained here, in this onConnect function, if we lose connection to our MQTT server, not really relevant when we're running on the same box as the MQTT broker, but it would be relevant if we weren't on the same box. If we lose the connection, then whenever we reconnect, which will be done automatically, we will automatically resubscribe to this topic. One thing that we should really be doing here, but we're not, is encrypting our connection to this MQTT server, as well as having some sort of shared key with this MQTT server to authenticate this server application. Without that shared key, as you'll see later on when we do the second half of this project, any server can send information to this MQTT broker. This is a very large security vulnerability and will absolutely be exploited later on in this course. So in this onConnect callback, subscribe to the topic, set up the callbacks for the left and right messages. These callbacks are over here. All they're doing is saying, yes, we got a message from one of the sensors. Yes, we got a message from the right sensor. The same for the left message, just saying we got a message for the left sensor. After that, we will connect to the broker, and set up our parking lot. So this parking lot is a class, just hold some data about the parking lot. What's the maximum occupancy? What's the current occupancy? for demonstration purposes, we set the max occupancy to 10. Then we enter this while loop, and we will never exit from this while loop. We call this client loop function, which will stay inside this function until we receive a message on any of the topics we're subscribed to. Once we exit that function, so we've received some message, we check, was the message relevant to what we're doing? Was it from one of the devices? Did our updated flag get set? If it did, we will set that to false again and work out, did we receive a message from the left or right sensor? If we received a message from the left sensor, that implies a vehicle is leaving. And so if we're able, we will decrement the lot's occupancy by 1. If we received a message from the right sensor, that implies a vehicle is entered. And so if we are able, we will increment the lot's occupancy by 1. We will then log that we're publishing data, form the data and message to be sent, and publish that to the display's MQTT topic. So the form display data and form display message functions are slightly interesting. Form display data forms the actual string that we want to display on our display. And so that will be spots, number of spots occupied, / maximum number of spots. That's all that will do. We need to base64 encode that, and then we will just return this data. We will then take base64 encoded data and form the display message. To do this, we take the message we're interested in, form the JSON object here. We want to confirm the LoRa packet. We want to publish it to the first port, or to the first port, and then our data is going to be the data that we've already base64 encoded, and then we will return this as a string JSON object. Then we publish that to the display MQTT topic with the message. The chirp stack server will then see that. It will see the confirmed port, set those up in the LoRa message, and then send this data here down to the display. And that is all we are doing inside the sensor code. So now we're going to go to a demonstration of the smart parking lot system in action. I don't actually have access to a parking lot to test this on the entrance of, and so instead I tested it in the cul-de-sac in front of my house. The way I did this is I placed the right sensor that would detect when vehicles enter, placed that facing the cul-de-sac, and drove a vehicle past it, and then verified that the server has seen that a vehicle is entered, and now the display is updated showing that one vehicle is in the parking lot. I then removed the right sensor and placed the left sensor facing the cul-de-sac and drove a vehicle in front of it, and then removed that sensor and verified that the server has logged there are now no vehicles in the parking lot, as well as the display also says there are no vehicles in the parking lot. So let's go ahead and cut to that demonstration video. Okay, so we're going to demonstrate this working. I'm going to go ahead and have my brother drive past in a vehicle. And now if you come take a look at this screen, you can see that we've registered one vehicle entering, and that also appears over here on the display. Make sure you get the display. Okay, now I will have my brother drive past again. And as you can see, we have also registered that a vehicle has left. And so we're now back down to 0 out of 10 spots in the parking lot. And of course, the display again shows that vehicles have left. And that's all there is to the demonstration. Okay, so a few closing remarks about this. Up here, you can see a link to a GitHub repository. All of the firmware developed for this project is available on that GitHub repository, as well as links to any libraries that I used. Additionally, I hope you noticed some of the rather poor security practices throughout this project. I want to reassure you that is in fact intentional. As you know, the second half of this course will be exploiting some of the security vulnerabilities in this project, and so I was careful not to fix any of them too early. I didn't want to limit my options at the end of the semester. But because all of the firmware is posted on GitHub, if you notice any security practices that you really think are too big, or anything that isn't documented in any of the firmware, please submit a ticket on GitHub and I will patch that. That is all I have for this presentation. Thank you very much for watching, and I will see you at the end of the semester.